Mihaela Albu to start the session. Over to you, ma'am.
Thank you very much for the introduction, and I'm happy to see the interest for this webinar. As you just heard, it is on the topic very relevant for what is happening now in the emerging power systems. And just because, as you see, it is as a distinguished lecturer from the Instrumentation Measurement Society program, please allow me for the beginning just to introduce very briefly this society. I'm sure that you know about it. I'm sure that you know that the logo and the code that is used for this IEEE society is the one from Lord Kelvin: to measure is to know. But also it's good to know which is the field of interest, and this is of course the science, technology, and application of instrumentation and measurement. We have members all over the globe, and you can see that most of the chapters, so we are organized in chapters. Most of the chapters are in region 8 and in region 10. So considering that I'm coming from Romania, which is in region 8, and you are based in southwest part of India, if I'm not wrong, this is a kind of connection. We have most of the chapters on Instrumentation and Measurement Society. There are several conferences. The flagship conference is I2NTC, which is usually in every May. And there are several other major sponsor conferences. I can also um, remind about the medical measurements and applications, but also on precision clock synchronization, as you see on the slide. However, there are also web workshops, dedicated workshops, and because I suppose you are interested in power systems measurements, I just want to recall that every September we have a workshop. It's called AMS, Applied Measurements for Power Systems, and we will celebrate this year the 10th edition. About the publications, the most let's say relevant and important considering the impact factor is transactional instrumentation measurement, but we have several articles on measurement in the magazine and also informative news in the INM newsletter, which is a quarterly publication. I am part of the distinguished lecturer program today in front of you, but I would like to remind that we have two very interesting awards. It's one of them is Graduate Fellowship and Faculty Course Development Award, and the other one is Best Dissertation Award. So I invite you and your team to apply for these awards. Usually the deadline is every beginning of March. There are several other activities. I will not bother you with this. You can find on the web page of the society. But also I'd like to remind that there are several technical committees working on standards, IEEE standards, but not only, as you know, IEEE and IEC, Technical Electrotechnical Committee, they work together already for several standards. I'm very proud, or let's say I'm happy, not necessarily proud. I'm very happy to say that one of the first standards ever with dual logo, IEEE and IEC, is the one issued 2.5 years ago on the phasor measurement units, which is somehow related with the topic today. There are several awards. Again, you can find them on on the web page. But considering the young specialist, I would like you to consider applying for the Berry Oaks Advancement Award and the Outstanding Young Engineer Award. Of course, all are open to you, but I'd like to underline these opportunities. So now I'd like to say that the plan for the talk today is, as you see, starting with pinning out which are the issues in the emerging electric power systems. And these are actually the smart grids, and why the measurements are important, what is so specific to measurements in smart grids, and to end up into a kind of mix, I can say, feelings related to the high reporting rate measurements, which is actually the topic of our talk. And then we will have some examples on the so-called unbundled smart meters and on the synchronized measurements, and example of the use of mixed reporting rates. So first of all, we shall look to what happened recently to the power systems in such a way that we ended up with this smart grids, which is more than a buzzword. It's happening all over the world. And I can say that it's not only what we immediately think of, which is the communication, digitalization, increased use of this digital information for controlling the grids, but it is mostly related to what I would call our greediness, the good greediness, to exploit the renewables sources of energy for obtaining electricity. And this, if you see here, this is a kind of a result of a European project that was investigating what will happen if in the future 100% of the electricity will come from renewable sources, and these are mostly distributed sources. Of course, you'll be happy to have reducing emissions of greenhouse gases, but this is possible only if we use power converters mediated energy transfer. I would like to call it like this. And also to face this intermittence of availability of the energy and by that the electricity. The main result, and this is governing all what we are speaking after that, is that there is much lower inertia available in the system because we don't have the rotating mass of the large traditional generators. And this means that if we want to control such a system, and this control can be done on a larger scale by these so-called wide area measurement and control systems, if we want to control, then we need time constants in the control comparable with the time constants that are now describing the phenomena. And these time constants are much lower, and even steady state is going below seconds. Until now, let's say that discrimination between steady state and quasi-steady state and dynamic conditions was done in the order of 1 to 10 seconds. Usually 3 seconds is let's say a timing characteristic for large power systems. It was. And this means that we need also measurements, as we see here, everywhere for obtaining the control, especially in these newly appearing microgrids, so newly structured regions of grids where we have lower capacity and load curves with lower, higher value. So we need much lower time constants, measurement time for getting the information. Until now, this is, yeah, sounds simple, but then let's take a look to what means measurements. And I'm sure that everyone recalls that measurement is a goal-driven process, that we need not only the measurement, we need a measurement system, and we need to qualify and define the environment. At the first glance, everything sounds very simple, but let's look to a very common measurement in smart grids, and this would be frequency. So we can say, okay, we want to measure frequency. This is identified, and then we need a frequency meter, so something that is providing the measurement of frequency. However, um, this new dynamic conditions, this intermittence caused by the intermittence of the availability of electricity, means that the frequency is actually not anymore constant. And we will see immediately what does it mean, or the measurements that will show this. And if we think about frequency, it's the inverse of period, and the period is characteristic to periodical signals. But what happens if this period does not exist anymore, because each period we have another value, so another value of frequency? Then what is frequency? It's not trivial, and just these days, actually at this hour, there are meetings of IEC committees dealing with definitions of frequency and rate of change of frequency for measurements required by the integration of distributed energy resources, for example. So first of all, we need to identify the measurement. If we are not able at least to identify its representation in our selected model, so coming back to the frequency, we can consider that frequency is the average over 200 milliseconds, like in the power quality approach. So we need to specify which is the model that we want to consider. Maybe the model is far away from the reality. This is life, but we have to specify. Then we have to find a measurement system, and then, as I said, we have to be sure that we use the measurement system or the measurement equipment in the right conditions. But how to control these right conditions, not to have influence factors? We cannot control everything, and especially there is something that we cannot control at all. And here, yeah, I used um, I'm liking very much a quote from the Professor Ferrero coordinated book in Wiley. There is something that cannot be kept constant, and this is time. And this is reflected in the dynamic unknown conditions which are far away, or putting our model far away from the reality. So wrapping up, the quality of the measurement that we will perform, it's described by a standard uncertainty according to our use of guide of expression of uncertainty in measurement, and has two parameters. One of them, or two components, one of them is the uncertainty associated with the measurement equipment. And this is usually only the one that we compute. Let's say you used a smart meter class 0.2, which is the norm in smart grids today. This means we can compute the uncertainty 0.2 divided by square of 3, for instance. So we know this, but we have to take into account the difference between the model that we consider, like constant frequency, and the reality. And this is this uncertainty, the model uncertainty. And if we look to this equation, we don't see the time. It's hidden. And it's hidden where? Exactly in these dynamic conditions that are describing the model. So what I would like to say is that it's good never to forget that we have to look not only to the measurement, the quality of the measurement equipment, but also to the appropriateness of this measurement to the reality, yeah, to the phenomena under study. You might say, why is so important? Because otherwise it's a pity. We are in the phase where we have advanced measurement systems. We can easily deploy measurements with sampling rates up to 1 megahertz, which is incredible. So until a few years ago, 10 kilohertz, 10 kilo samples per second was a kind of limit. So we can deploy advanced measurement systems and associated data communication, but we use some still traditional models for the smart grids operation. And the result, sorry for this noise, the result is that we cannot achieve an optimal control of the energy transfer. You'll say, well, what's the problem? It's not optimal. Yeah, but smart grids, they appear exactly for that. Smart grids means putting money and intelligence and communication and digitalization to achieve an optimal control of the energy transfer, not to lose, to increase the efficiency. And just because we don't use the right models, we fail to achieve this. And as I said, it's a pity. Now, just to take a, a look to something else that is also related to the high reporting rate measurements. In power system, we usually deal with voltage, currents, analog. Yeah, we still have analog energy transfer. And for those quantities, we have a model, let's say a periodical model, and we can define the so-called instantaneous value. Now, at each moment, we can know, now we can measure the instantaneous value of voltage or current. However, we deal with active power, reactive power as well, but power. And by definition, although there are a lot of definitions, but it's the only one that is still agreed everywhere because it's coming from physics. By definition, power is an integral quantity, which means that we cannot associate an instantaneous value to the power. If we report a value of the active power measured, let's say at a moment tk, then we have to say, what does it represent? It represents the average of so-called instantaneous P of t. Yeah, no one is speaking about it, but it's this active power calculated, estimated over a time interval t here, or and reported later or the end of the time t, or when. So I'm just trying to say. So this value has no meaning if we don't know what is actually this power, on what time window it was calculated. So even this is said, I just want to say that from all the possible signals that we can encounter in reality and in power systems, which are much more related to the non-deterministic signals, we still use the models associated with the periodic or maybe quasi-periodic waveforms. And what I would like to say and to end this part is that in smart grids, most of the time we speak about data, about a lot of data, even about big data. But we shall think that and be cautious, because these data are only the last form of the digital signals which are obtained from the analog signals describing the reality. And here we have to think to 2 points, and not only to avoid aliasing, so to select the filter, the low pass filter appropriately for the sampling frequency. This we know from classical measurements, but also to recall that not having periodicity, not having steady state as we had before, the use of the time windows that anyway has to be applied in order to avoid uh, let's say, frequency leakage, Gibbs effect, whatever you want to call. So when we use these time windows, we have to think to the periodicity or to the time that in uh, the phenomena that is analyzed, like let's say frequency power, active power to frequency control or frequency restoration, we have to think which is the time constant for that phenomena, and then to use the to select the window in accordingly. So in this way we avoid distortion in frequency domain. Now, this being said, we can say that we are in a field where we are a little bit lucky because we should not have that much data, because people for more than 100 years considered that signals are sinusoidal, and therefore we can operate only with a few parameters. So instead of operating with a whole signal like UDT voltage, we operate with a mean value, average value, or much more used, the root mean square values. You have here the definitions, of course, in analog and in digital form. Uh, what is this? This is the first step of information compression that was done so many years ago, and we inherited, unfortunately, in the analog way that we knew to make measurements. So first measurements have been like ampermeter or voltmeter analog measurement instruments, and they knew how to map a periodic signal, usually a sinus wave periodical signals, to one value, and that value was the RMS value. However, this type of information compression is extremely lossy, and is lossy as long as, of course, we don't have to deal with known sinus wave or sinusoidal or even periodical waveforms. And if we look a little bit to what is happening, then we start to think that we need um, to identify these sources of not necessary loss of information. So what is in this figure? Actually, what we are interested to know by measurements is this phenomena where we have the information source, and then we translate into the model, as I spoke about the frequency, and we consider that the received signal, let's say a voltage for which we want to, voltage signal for which we want to measure the frequency in this input of the measurement system. What is in between is still full of potential errors. For instance, as Dr. Kirkham uh, mentioned and also named it, is a semantic noise source. Is again this model, imperfect model realization of what we want to measure. But on the communication to the measurement system might be also a source of noise. And here can be listed also the analog to digital converter and the sampling and the number of bits that we selected. And then we have this measurement result, which is, as said, a compression of the original information. However, in power systems and especially in smart grids, this data processing does not end here, because from the measurement results, we apply further algorithms, and these are filters, low pass filters, sometimes with unknown characteristics, to obtain the final reported measurements. So what is coming, what is arriving to us as users are these reported measurements. You might ask, what is in between? And this is the so-called aggregation. Most of the time is time aggregation, which is standardized sometimes and sometimes not, known sometimes and sometimes not, even in the large, let's say, substations with SCADA deployed. And you might ask yourself, why this? Because it happens that traditionally, the control and the monitoring of what is happening in grids was done in the control centers, and we wanted to have a kind of human uh, control. I'm not speaking about protection. I'm speaking about the measurements and about the monitoring of the processes. And the human brain and eye has a time constant larger than the time constant of this phenomena, which is milliseconds. So because of the distance from milliseconds, okay, the interval, not the distance, from milliseconds to seconds, it was proposed and in place this further aggregation of information. In the end, we can say that measurement is anyway a loss information compression, but in smart grids, the paradigm is that is additional data compression, which is hidden. And we have to rebuild or to know it or to know the effects of that. So you might ask yourself, because this aggregation is very simple. If we think to the power quality, the voltage that is reported, the RMS voltage that is reported at the first glance, is the average squared average of 10 individual voltage RMS values, yes, over 200 milliseconds. Then the second reporting is over 3 seconds, and then about 10 minutes, and then on 2 hours. So this averaging is something very simple, but is it's a low pass filtering. And you might ask yourself, why? If we know that this introduces so much additional uncertainty, why shall we use it? Because not long time ago, such a procedure had the great advantage great advantages to reduce the number of reported values and to reduce the associated uncertainty. Because if we have, let's say, 10 measurements of the voltage and we report only the square of those 10 measurements, the uncertainty associated with the results is lower, well, 3 times lower, square of 10. So at the first glance, we say, oh, this contribution to the uncertainty of the individual measurement equipment is lower. So it's great. But we forget that in the same time, the model uncertainty, the definition uncertainty is increased, because in this larger time interval, the variability of the voltage that we measure, it's higher. Now it's higher. It was not before. We did not care about these tiny things in the 3 seconds time window, but now we have to care about. So the end idea is that this decimation introduces an additional uncertainty, which is associated not with the measurement, but with the meaning of the resulting quantity. So we capture here. Here are some examples to demonstrate that, of course, we had reasons to do this. We have reasons. This is what is here is a LSPEC measurement equipment, which, by the way, goes up to 1 megasamples per second sampling rate. And for instance, if we use it only to 150 kilohertz sampling, 1 minute, one channel means one measurement. It was the voltage, 120 megabyte. If we use the power quality approach, so we report one RMS value every 3 seconds, the same phenomena is compressed to 40 bytes. So of course, there is a reason to use this type of aggregation, but at least to be aware of the downsides. Here is an example where this type of aggregation is also useful because it might reveal information that otherwise would be lost. So otherwise not necessarily would be lost, would be difficult to interpret. And here we have a synthetic signal, actually is mimicking a a current waveform from a microwave, but can mimic also the current waveform from a distributed energy source on a cable where we have PV, and we can see that analyzing. Even if we start to analyze the waveform with highest reporting rate, we will not identify the amplitude and the presence of frequencies on some specific time interval. So here is time on the horizontal, and here is the frequency component, so where they can come into place and which are the amplitudes if needed. But here the frequencies are usually very, very useful to investigate. So it's a kind of accurate time frequency analysis. Here is done with the Hilbert-Huang method, and can reveal phenomena that are occurring into the analyzed network. So not always aggregating the information is bad. Now, some examples on high reporting rate measurements. And these are examples with smart meters. This is a special smart meter where we call it unbundled, where we discriminate between the metrology part and the communication part, which is very cheap to obtain. We deployed in several systems, such meters, and here just to show that if we would report as usual the electricity consumed every hour, so with hourly reporting, we don't know much. For a household, for instance, power profile, this is a 1-day power profile, and here is the detail obtained again with 1 second. So high reporting rate meter measurements with 1 second compared with hourly or even worse, daily reporting. Here, what we have here, it's a microwave power profile in time, and it's interesting to see that even a poor microwave can influence the voltage level if we are in a microgrid or in a weak grid. So when it's the power profile, there are about 3 volts RMS value lower voltage. The same what is happening in one normal household. These peaks are simply the turning on of the refrigerator, and this duration is 4 seconds. We have to capture. And here what we have a simple calculation of the information loss. For instance, for this day, yeah, this is again 1 second reported power profile of a average household consumer, household actually. And if we compare with what we would have known if we would have reported hourly, then we lose 140% of the information. If we would report every 10 minutes, and some smart meters are going towards 10 minutes or 15 minutes, then we'll have lost 100% of the information. If we report every minute, then we'll have lost 30% and we'll be a little bit happier. However, for another day, this is a working day where it was used also the washing machine. Yeah, this is the power profile every second. If compared with what would happen if we would report hourly, we would have lost 113%, while each minute 64%. Already a loss, high loss of information. Considering that in microgrids, which are part of the smart grids, the future, way of controlling the large grids, we have of high importance this type of variability of both generation and consumption. Here it was only the consumption, but we could have add also the PV and so the generation. We end up that hourly measurements, 15 minutes measurements in case of meters are of no use. We need 1 second reporting rates. Here are other examples from student dormitories. Here are examples from the frequency measurement with much higher reporting rates, and this is up to 50 frames per second. And these are done with the phasor measurement units. We will not speak in detail on phasor measurement units because they are used in wide area measurement and control systems for controlling large systems. However, until recently, they were the only measurement equipment that were providing with high reporting rate every 20 milliseconds information, yes, aggregated because it's RMS, on what happens with voltages and currents in a specific node. So from this point of view, the byproducts of PMUs, which are frequency and rate of change of frequency with high reporting rate every 20 milliseconds are of very high, very good use. And here we have an example of measurements provided by our PMUs located in 4 different nodes, and we can see that frequencies are different. And this is not the error because the measurement is with 1 ppm hertz maximal error, so it's extremely precise. This shows that frequency already is not a system value, is not the same everywhere, in a defined system, even large power system. And here we have other examples of such measurements with the PMUs using, again, high reporting rate. Here is an example where high reporting rate can help in analyzing dynamic phenomena. Here it was analyzing of the response of several controllers of large units in Romania. This is the map of Romania after a huge generation loss caused by lighting. And we can see in each location at high voltage, actually, we can see the frequency variation, and analyzing, we can again establish the best control system. We can look also to the examples of how to exploit these high reporting rate measurements. And the best, in my view, example is to look into state estimators. And usually, as I'm sure that you know, the measurements, so the classical state estimator, which are run at the system level, use SCADA provided measurements, not synchronized, however, timestamp, but not using always a synchronization time tag. And they are provided at intervals between, at second, yeah, time interval, 2 to 30 seconds. And in order to use a few measurements and calculate, derive the other values of voltages in all the nodes of the supervised system. Of course, one can take into account several models, usually balance system and no time skew between measurements. This is a huge simplification. And there are today two ways of deploying or to perform state estimators, either linear state estimator, which means measurements provided by the PMUs and then simply calculating the rest of unknowns, or because it's expensive to have PMUs in all nodes requiring full observability of a system, of a large system, or to use hybrid state estimators. And here is the problem, is our problem. Because in hybrid state estimators, we use measurements provided by the PMUs and measurements provided by the classical SCADA systems. And the question is how to combine them. How to combine information coming every 10 or 20 milliseconds with information coming every 3, 4, 5 seconds. Is not about the timing, is about the meaning behind those measurements. And the meaning is translated usually into a associated uncertainty, because we remember that uncertainty of the measurement has two components: the measurement equipment itself and the model associated. And this type of measurements, they use different models. So here we have an example where we want to correlate measurements coming from the PMUs, from the micro PMUs, and from the smart meters, which 1 second. We have some specifications here just to know that the reporting rates we are looking for are the highest at the PMU, phasor measurement unit, can attain even 100. Yeah, let's say this is the highest. For the micro PMU, if we use in distribution network, it's in the order of 1 second. I said 3 seconds before, but let's make it in the order of 1 second for the SCADA provided measurements. The classical energy meter is providing hourly or every minute or every 15 minutes information. 1 per 900 would be 15 minutes. 1 per 60 would be 1 minute reporting rate. And the smart meter in that form that I was speaking before, that we realized, unbundled smart meter, we can obtain up to 1 second or 1 reporting rate, each second another value. And the resolution of the information associated, for instance, for frequency, it's different. It's much higher in case of the PMU. It's much lower in case of the classical measurements. And then we have to combine them. Of course, we can think to various ways of combining, which means either decimation of the PMU high reporting rate measurements up to the 1 second smart metering provided measurements, or we can oversample the let's say, artificially oversample the measurements provided by the smart meters in order to obtain similar rates as the PMUs. But this downsampling or oversampling can be done in various ways, and each way can inflate differently the associated measurement error. And here are some examples of how we can do this with the PMUs and the smart meters if we go to the 1 second metering reporting rate. I would like to wrap up because it would be great if we can also have some questions. I would just want to recall that in order to control smart grids, we need faster measurements today. We need to develop information processing methodology to extract meaning and knowledge out of the data, and this means that we have to know the models behind the measurements that we are using. In order to do this, we need accurate models, but most of time, what we would need, and this is my call for several years to the signal processing community, we need other solutions for data compression. This RMS and this aggregation ways of achieving lower reporting rates, these are outdated. We can use other proper data compression techniques, therefore I'm really waiting for the new measurement equipment with higher reporting rates, like the smart meters, that are able to deploy compression algorithms. By the way, to my knowledge, the equipment that I was just saying that has a very high sampling rate that we are using for testing in the lab a lot of algorithms is the only one, to my knowledge, that is delivering the information. So all this data, I said 1 megasamples per second, together with data compression and encrypting algorithm. It's one way of going further. Synchronized measurements, they are of high help. We spoke about the phasor measurement units only in the sense that they provide very high reporting rates, very high for our use. I did not make comments that in the future we will face much higher reporting rates because the digital substations will use the simple point-on-wave representation of the signals. So we have to expect even higher reporting rates. And in the end, we spoke about state estimators as an example of the need of merge measurement data coming with heterogeneous reporting rates. Thank you very much. I hope that at least I'm in time, and I'm waiting for your questions, because I think
Thank you so much, ma'am.
Session. Thank you.
Now the stage is open to questions. Participants may unmute your mic or use the chat box for clarifications of doubts or any questions.
I see a question in the chat. And I think that it was the Well, the question is about if we have some artificial intelligence algorithms for reporting. Um, well, usually these algorithms are used after having the data. So we are still in the measurement area. And measurement means that I have to provide as measurement equipment to or the measurement equipment has to provide two values. One value is the value of the measurand, yeah, let's say 230.4 volt. And the second information that it's mandatory to be provided together with the measurement value is the standard uncertainty associated with that measurement, which or the limits of errors. Let's say it's a kind of explanation of the highest limit of error. After that, any algorithm that we will do for controlling, for monitoring, for doesn't matter what with the data, has to take into account these two numbers. And unfortunately, the uncertainty, the measurement uncertainty is inflating. Yeah? By any calculation, it's inflating, it's larger. And this has to be taken into account. So yes, we need artificial intelligence algorithms for processing the information that is carried by the measurements. But I'm afraid that before giving the measurements away, this is reporting, yeah, we already polluted the information. We already lost some information. And we just have to tell the user, hey, you will take the 230.2 volt measurement, but you know, is the uncertainty associated, it's 20%, it's not 1%. We have to announce somehow. This was my, yeah, uh, my intention. Yeah, this is another question if we are using virtual instruments or standalone equipment for measurements. Well, measurements have to be real, yeah, have to be well done with standalone equipment, because measurements to perform a measurement is a practical activity, yeah, it's not only mental activity, that is estimation, for instance. So we use a measurement chain, and in our field, yeah, we want to measure what is happening into the power system, which means that we have to interact with this power system that we want to study. So it's a real measurement equipment, real, of course, everything is real. So a standalone measurement equipment. But then the problem is that inside the measurement equipment, there is a tiny decision block or processing block that is deciding, oh, I will not give you every millisecond the information because you will be tired, you, the user. Yeah, I will make an average and I will give you the average every 10 minutes. Just be happy. And we will read every 10 minutes the value and we will see, oh, yeah, this is the measurement value. What I want to say is that we have to question ourselves how this reported value that is arriving to us, to the user, now even in a control system, how was obtained. It was measured every 10 minutes, or it was measured continuously and then made an average or I don't know what and reported every 10 minutes. The difference is huge because averaging is filtering, and filtering, we know, is loss of information.
Thank you, ma'am, for clarifying the doubts. I hope all the doubts are cleared. Now I think there's one more question. No, okay. So let's wind up our session. As we end today's event, I would like to express my sincere gratitude to Dr. Mihaela Albu for the informative and interesting session, and we are really thankful for having you with us, ma'am. I would like to thank all the participants for joining the event. Your immense support and cooperation has led this event to be a huge success. We have sent the feedback form in the chat box for the participants. Please do fill the form for attendance. And thank you all for your presence. The session is officially concluded.
Thank you very much. Thank you. And congratulations for the 56th talk. Congratulations.
Okay, thank you, ma'am. Thank you from Malabar Subsection.
Thank you.
Thank you, Archa.
Thank you, sir.